Hello and welcome to this video about triggering. I am Eva, a machine vision specialist at IDS. In this video, I will give you an insight into the countless trigger possibilities that the IDS cameras offer. Triggering is a fundamental component of operating cameras. Many high-precision applications in machine vision require cameras to capture frames at a very specific point of time. The most common application is presumably to trigger an image capture via a signal at the hardware input. In practical use, for example, goods travel along a conveyor belt. Typically, a light barrier is triggered when an object passes in front of the camera. But there are many more trigger options available for our IDS vision cameras. Simple automation tasks can be solved by a smart combination of the provided function blocks, which can be put together similar to the connection principle of the famous Lego bricks. These modules can be, for example, counters, timers, and many more. They provide a fast and robust control method and eliminate the need for external control logic. Some of these functions are defined in the vision standard. In addition, IDS cameras offer further functions that go beyond the standard and with which more demanding automation tasks can be implemented. In this video, we will take a look at the individual modules and how to combine them for specific tasks. Stay also tuned for general trigger tips and live demos of specific trigger use cases. The trigger use cases from this video and many more are also described in our tech tip, Triggering According to the Lego Principle, on our webpage. So don't hesitate to also take a look here. Let's start from the beginning. What is necessary to configure a valid trigger setup? First, you need to decide what kind of action you would like to trigger. For example, you want to start the exposure of an image with a trigger. The action you would like to trigger is the trigger target. The available targets can be selected via the trigger selector. The trigger selector is a parameter that contains the list of available trigger targets of your specific camera. We will look at the different trigger targets later. After defining the target, you need to specify what the source of the trigger signal should be. So what kind of event or signal should the camera listen to trigger the required action? There is a huge amount of signals and trigger sources available, which we'll look in a few minutes. You also have the possibility to define how the signal coming from the trigger source should be processed. This Lego brick is called trigger configuration here. You can, for example, put a delay on the signal or say that the camera should only react on every nth signal. After configuring the trigger setup, it is necessary to put the trigger mode of your trigger target to on in order to make the configuration active. Also, there might be additional parameters that you want to adjust, like exposure time or gain. The final step after the parameterization is to call acquisition start. This command makes the sensor ready for image acquisition. After calling acquisition start, the camera will actively wait for and react to trigger signals. Before we go on to our first trigger use case, let's have a deeper look at the different trigger components. Let's start with the trigger targets. Camera activities are probably the most common trigger target. Camera activities are actions like starting the exposure of an image, so the exposure start, or the whole acquisition, or end it, or in line scan mode, trigger a single line. This is a screenshot of the IDSP cockpit where you can see how the parameters can be accessed. In the GennyCam standard, the camera parameters are called nodes. There are so-called selector nodes that contain a list of available entries. In our case, there's a trigger selector from which we can select our desired triggered target, so the camera activity. It should be noted that not every camera has every target, depending on its feature scope. You can check this easily for your specific camera when reading out its trigger selector. Some trigger targets can also be combined on one trigger setup. For example, with some cameras you can use the so-called trigger-controlled exposure. In this case, there is no preset exposure time, but the trigger pulse width determines the exposure time. So the rising edge of the trigger pulse will reach the trigger target exposure start to start the image, and the falling edge of the trigger pulse goes to the target exposure end to terminate the image capture. Another type of trigger targets is the control of internal automation modules. There are different modules available to support your trigger task. Counters can count incoming trigger signals when being used as a trigger target. We will see later that they can also be used as trigger source and send a trigger signal when a pre-programmed number has been reached. They are activated, started, and can be also reset to 0 by trigger signals. The reset can also be performed manually in the IDS Peak cockpit or via the Peak API. This can be used, for example, to perform a predefined number of exposures or to abort after a certain number of failed exposures. Another automation module is the timer. Timers can be started via trigger signal and then clock a predefined length of time, sending a signal in return once the time has passed. The timers can be used, for example, to keep the camera in acquisition mode for a defined period of time after having been activated via hardware input and then deactivating it afterwards. Some IDS cameras have an internal pulse generator which generates a square wave signal in the frequency range from 5 Hz to 100 kHz. The periodical pulses can be used, for example, to perform exposures at a specific frame rate or to control an external light source. The PWM, the pulse width modulation, can be a target and therefore be started via trigger signal and afterwards be a trigger source for further actions like image capture. Some cameras also support the sequencer module. When using the sequencer mode, up to 12 sets of different parameters can be created for image acquisition, whereby the parameters exposure time, gain, and the offsets may be adjusted as required. The sets are then automatically executed in a defined sequence. This allows fast parameter changes for image acquisition. When triggering, the sequencer sets other trigger targets that can be triggered by different trigger sources. If you want to know more about the sequencer, check out the video from my colleague Eric about the sequencer. It is called How to Easily Capture Image Sequences Without Complex Coding Effort. Hardware outputs can also be trigger targets. When the target is a hardware output, this means either the flash output, it is called line 1 in the IDS Peak software, or one of the GPIOs. These are called line 2 or line 3. These targets can be used to, for example, start a flashlight or another external module. Camera events can also be trigger targets. You can activate different events that then can be processed by the connected PC. There are events like exposure start, exposure end, or about missed triggers, critical errors, and some more. Events are a special case of trigger targets, as you don't have to specify a trigger source by yourself. You just activate the event, let's say exposure start, and then the trigger process happens automatically inside the camera. The exposure start of the image is the trigger source that then triggers the event, with the event being the trigger target. Let's now have a look at trigger sources. The operations generating a signal are called trigger sources. There are 3 different types of trigger sources. The first types are external trigger sources, such as signals coming from hardware OS and software inputs. Our vision camera models provide electrical pins that transfer electrical signals and work as trigger sources. There is, on one hand, a dedicated trigger input with an optocoupler. Also, there are 2 more pins, the GPIOs, that can be used as inputs. Here we already see that some components can both be trigger sources and trigger targets. A GPIO can be a trigger source and as well a trigger target that receives the signal from the camera. There are also some more modules than the GPIOs that can fulfill both jobs. If no hardware trigger signals are available or necessary, a software trigger can also be used. There is a dedicated software trigger that, once executed, starts the exposure of an image. But you have also so-called user outputs, a powerful possibility to simulate an external trigger signal. If you want to test an application that depends on a hardware trigger, but you don't have a working hardware signal set up yet, you can simulate the hardware trigger signal. To do this, you take advantage of the fact that one of the user outputs can be assigned as the signal source to the trigger input, or the GPIOs. This user output can be set manually and subsequently also the hardware I/O level. The following Lego bricks might sound familiar to you, as we have already looked at them when discussing trigger targets. Counters, timers, and the pulse width modulation can not only be trigger targets, they can also be a source for a subsequent action, like the exposure of images. The same applies to camera inherent acts like start and end of acquisition time or exposure time. While we have seen these acts as trigger targets before, they can also be a source. For example, a counter can be increased when the exposure of an image starts. So that means the counter is the target here and exposure start is the source. Depending on the source, the signal is either a short pulse triggered by an event, like a start signal, or a continuous signal, for example, while something is active or inactive. Likewise, some targets need a pulse as a signal, for example, to count up a counter, or a permanent signal, for example, for a hardware output. Some targets that need a pulse can also process the status change of a continuous signal, letting you choose between detecting rising, falling, or both edges. Camera action trigger targets like the start and end of the acquisition mode, the exposure or the line of frame trigger allow additional parameters to be set, which we call trigger configuration here. A trigger divider tells the target to react only to every nth trigger signal from the selected source, so it will ignore all signals in between. A trigger delay adds a delay of 0 to up to 16 seconds between reception of the trigger signal and execution of the requested action. As seen before, sometimes we can choose the trigger activation, which determines what kind of signal the target should react to. Let's come to the hands-on part and configure different use cases together. Let's quickly remember the chart from the beginning with the minimal requirements for a valid trigger configuration. We need to define the trigger target, the trigger source, and depending on the use case, a trigger configuration. The trigger mode has to be set to on, and after setting additional parameters, we have to call acquisition start to make the system ready for image capturing. One of the most common and also simplest use cases is a non-cyclic image acquisition. For example, different types of parts are transported on a conveyor belt. A light barrier triggers the image acquisition of the parts to read out barcodes for part identification purposes. So, what are our requirements and boundary conditions for this use case? Non-cyclic trigger signals occur as a result of different parts and distances. The trigger signal, so the trigger source, can be a hardware or a software trigger, for example. This signal time diagram of the non-cyclic image acquisition shows what needs to happen for this use case. With the acquisition start command, we make the camera ready to wait for incoming trigger signals. A quick excursion here, we will use the terms exposure start and acquisition start a lot of times in the following section. So here's a quick differentiation between those two. With acquisition start, the camera prepares itself to be ready to take images. When being in trigger mode, the camera starts to wait for trigger signals after the command has been executed. When the camera is in free run mode, it will automatically and continuously start to take images with a defined frame rate after acquisition start has been executed. The exposure start, on the other hand, is the event when a new image is actually taken. For example, in this use case, one trigger signal will start the exposure of one image. Immediately after the trigger signal, we want the camera to start the exposure of an image. To produce sharp images, we need to preset the exposure time accordingly to the lighting conditions and speed of the conveyor belt. Precisely one image image is captured for each trigger signal. During the acquisition and readout time, no further trigger signal is accepted. After all images have been taken, we can perform the acquisition stop command. So how do we need to configure this scenario in the IDS Peak software? I have prepared a short schematic we can look at before switching to the IDS Peak software. Let's have a look at our already familiar scheme of trigger targets, the trigger configuration, and the trigger source. Our trigger target is exposure start, as we want to start the acquisition of an image with our trigger. This trigger target can be chosen via the trigger selector, which we will see in the IDS Peak cockpit in a minute. The trigger mode needs to be on. If it's off, the camera would be in free run mode, continuously capturing images with a defined frame rate. We do not need a special trigger configuration like a trigger delay or a trigger divider, so we leave everything default. The trigger source will be line 0 in our case, but it could also be one of the GPIOs or a software trigger. To finish the configuration, we need to make sure that the acquisition mode is set to continuous, which means that after capturing one image, the camera will wait again for the next trigger and not stop to wait for triggers. Continuous is also the default acquisition mode of the camera. Also, we need to set a good exposure time for the camera that matches the needs of our application. When everything is configured, we can execute acquisition start to make the system ready for capturing of images. Let's now switch to the IDS Peak cockpit and do the configuration here. I have already connected a USB 3 camera, and next to me I have a demo setup with a small conveyor belt and a light barrier. I have connected the camera and the light barrier, so when an object passes the light barrier, a trigger signal will be passed to the trigger input of the camera. Now we have to configure the camera to process this trigger signal correctly. The best way to do the configuration in the IDS Peak cockpit is, in my opinion, via the generic parameters section. We have the whole list of available camera parameters here. A lot of functionality can also be configured via the menus on the left side, but here you have the complete list and you can easily search for a parameter. The generic parameters are also an easy way to check which modules and parameters your camera provides, as not all features are supported by every camera family. So, as we already said, in our use case now, we want a trigger selector to be exposure start, so our trigger signal will start the exposure of an image. This trigger mode needs to be on. It has to be noted that most of the parameters can only be adjusted when the acquisition is off, so we have to do this here before adjusting a parameter. Now we can set the trigger mode to on, and the trigger source will be line 0, which is our trigger input. Also want to set an exposure time. I have already set a very small exposure time of 2 milliseconds. And the acquisition mode, as you can see, is already continuous. Now we can start the acquisition again. And I will also start my conveyor belt. And we can see that every time a Lego brick passes the light barrier, one image is taken. Okay, great. So let's come to our second use case. The second use case I want to show you only differs from the first one in one parameter. In some cases, the image capture must be started with a delay. For example, in a conveyor system, when the trigger sensor cannot be mounted next to the camera for constructional reasons. The time delay then depends on the conveyor speed. So in this case, the signal time diagram only differs in one aspect. The image acquisition starts the specified exposure time with a delay, the trigger delay, with respect to the trigger signal. The trigger delay time can be configured in microseconds from 0 to approximately 16 seconds. no further trigger signal is accepted during the trigger delay and acquisition. So also the parameterization of our first use case only needs to be adjusted by one parameter, the trigger delay. Let's switch back to the IDS Peak cockpit, where our first configuration is still active. To be able to adjust parameters, we have to turn off the active acquisition again, and now we can adjust the trigger delay. Okay, I have now chosen a value of 300,000 microseconds, and let's now see what happens when I turn back on the acquisition and start the conveyor belt. We will now see the Lego bricks on a different position in the images compared to before, because there's a wait time between the trigger signal and exposure start. In this time, the Lego brick has already moved on. Okay, let's turn off the conveyor belt again and come to our third use case. Now, let's bring the internal automation modules come into play. In our next use case, we will use a counter as trigger source. Some applications need a specified number of images taken. For example, when a camera is used at a set of traffic lights to record the behavior of drivers upon crossing the stop line, while the lights are on red. A series of images with the adapted frame rate allows you to draw conclusions with regard to speed, the braking action, or a change of direction. This allows you to differentiate between a driver who accidentally crosses the stop line slowly and then stops, and one who commits a real traffic violation and fails to stop. So, what do we want to achieve? A defined number of images are captured for each trigger signal. The image series is captured at a specific frame rate. You can see that the signal time diagram now gets a little bit more complex as we add the counter as an additional module. What is also different now is that our trigger signal from outside is now used to start the acquisition and end it automatically when the required number of images is reached. The start of the acquisition lets the camera start in free run mode, which means that the single images or the exposure of the single images are not triggered by a signal configured by us anymore. The camera takes them automatically in free run with a frame rate that we have defined before. The counter counts up every exposure of a new image. When the specified number of images is reached, the acquisition is stopped automatically by the counter. The trigger signal to start the acquisition is a software or a hardware trigger, for example. The exposure time and frame rate must be set beforehand, and no further signals, as always, are processed while the counter is active. Again, let's have a short look at the schematic before configuring the use case in the IDS Peak cockpit. As before, we need to make sure that the acquisition mode is set to continuous. Also, we need to set a good exposure time that matches the needs of our application. And in addition, this time we set the desired frame rate with which the images will be taken. In our counted image sequence, we have more than one trigger target to trigger. We need to trigger the acquisition start command, the acquisition end command, and we also need to trigger the counter and define that it should count up the images that are taken. For this configuration, we only need one trigger from the outside to start the acquisition. The rest of the task is then handled automatically by the internal modules. To initialize the task and to trigger the acquisition start, we can again use a hardware trigger on line 0, which we will do in our case, or we could also use the GPIOs or a software trigger. We need to specify that in the trigger source. The trigger configuration can stay default as we don't need a delay or a signal divider, and the trigger mode for this target is on. The second target is the end of the acquisition. We want to end the acquisition when a defined number of images is reached. Therefore, we choose the counter 0 end, as a trigger source. The counter 0 will end when it reaches the specified number of images. Last but not least, the counter configuration. we have 2 counters available, but only need 1, so we choose counter 0 via the counter selector. We set the desired counter duration, for example 3, so the counter will end after 3 images. Also, it is required to define a counter reset source to make sure the counter is reset, to be then used again. We choose the counter trigger as reset source, so the counter will reset itself after it is done and we don't have to perform an extra step. Now we have to define the source that will trigger the counter to be activated. This is the acquisition start of the camera. The counter event source is the event that lets the counter count up. In our case, we want to count up when an image is taken. So exposure start is the right thing to choose here. Let's switch back to the IDS peak cockpit again. We still have our old configuration here, so we put the trigger delay back to 0, and we put the trigger mode for the exposure start to off, because we do not need the exposure start trigger. And now we can parametricize our trigger targets. So first, the acquisition start. Here, the trigger mode needs to be on. The trigger source is the line 0. So when a LEGO brick passes by on the conveyor belt and passes the light barrier, it will trigger the line 0, and this one will start the acquisition and therefore our image series. We also need the trigger target acquisition end. Also here the trigger mode needs to be on. And the trigger source here is counter 0 end, because we want to end the acquisition when the counter has finished. Now the counter configuration, we can search counter here to have all the parameters visible in the list. So we have 2 counters, but we choose counter 0 here. The counter duration, let's set it to 3 images. The counter reset source is the counter trigger, so it resets itself automatically. And the counter trigger source, so the source to activate the counter, is the acquisition start. And the counter event source, so the event on which the counter should listen and count up 1, is the exposure start. Okay. Now we need to choose our frame rate. Let's put it to a very low frame rate so we can see the effects better on the conveyor belt. Our exposure time would still be fine. So we are ready to start again. So we can start acquisition here, make the system ready, and start our conveyor belt again. So what we now see, that there are 3 images taken of each LEGO part. After these 3 images have been taken, the counter is reset again, so when the next LEGO brick comes by, the image series will start again and also produce 3 images. So this worked out very well. And we can stop the acquisition and our conveyor belt again. The next application might seem a bit similar regarding the way of configuring it, but we will use a timer instead of a counter, and it will take images with the maximum possible frame rate. Imagine you want to examine the impact of a water drop on different surfaces. To do so, acquisition is always triggered if a drop falls within the image area. In this case, acquisition is maintained at the maximum frame rate for a specified time in order to document the behavior upon impact. For this use case, we want to capture several images, so as many as possible, in a specified time. The image series is captured at the maximum frame rate that is possible with a preset exposure time. A timer is used as a tool for the image sequence, which stops the capturing of images automatically when the set time has elapsed. When looking at the signal time diagram, we start the acquisition by a command, not by a specific trigger source. So this is similar as in our first and second use case. the timer is started by an external trigger, which is executed when the drop passes a light barrier. The start of the timer also starts the image capturing. When the timer ends, this is the signal that no further image will be exposed. The timer can be started again and again, and the procedure performed all over again until the acquisition stop command is executed. And as always, no further trigger signal is accepted while the timer is active. Let's switch over to the configuration scheme. We first need to define the acquisition mode to continuous and our exposure time. The exposure of an image should be triggered as fast as possible as long as the timer is active. So we put the trigger mode for exposure start to on, and we select the timer 0 active as trigger source. The trigger activation is level high, because as long as the timer is active, this means that the timer signal is high. As soon as the exposure of one image has finished, a new one will be triggered, because the timer is still active and therefore the signal high. The trigger mode needs to be on, and the timer is configured as follows. You have to define a duration and a trigger source that starts the timer. In this case, this is our external trigger that sends a signal when the drop we want to capture passes by, or in our case, when the Lego brick passes the light barrier. The timer gets activated when our selected trigger source shows a rising edge. Let's switch back to the IDSP cockpit. I can't demonstrate a falling water drop today, so we will again use the conveyor belt with the Lego bricks. We still have our counter configuration here, so to be sure that nothing is active what we don't want to be active, we first reset our camera to the default settings. I can do it, for example, here on the left side, and just click load for the default user set. And now we can freshly start with our timer use case configuration. So the trigger selector exposure on, exposure start should be on. The trigger source is the timer 0 active, because we want to capture images as long as the timer is active. There it is. And the trigger activation is automatically level high, because there's only level high and level low as options. To configure the timer, we search for timer. We define the timer duration to 1 second. And we say that the timer trigger source should be line 0. So every time a Lego brick passes the light barrier, the timer will start. And the timer trigger activation is rising edge. Now we have to check our exposure time, because we have reset the camera to default values. So let's put that back. And now we're ready to start again. Let's click here to make the system ready for acquisition and start our conveyor belt again. Now we can see the Lego bricks passing by, and it seems almost like the Lego bricks are running by like a continuous video. This is because for a defined period of time, images of the Lego bricks are taken with maximum frame rate, which is very fast for this camera. So also this trigger use case has performed very well. So let's stop the conveyor belt again. And now we have only seen a few of the countless possibilities to combine camera functionalities for trigger purposes. You could also build more complex structures, like for example, combine timers and counters and use more than one timer and counter, because you have 2 timers and 2 counters available. As you can see in the timer and counter selectors, these modules can be trigger targets and trigger sources also for other timers and counters. All the trigger use cases and many more are also described in our tech tip, Triggering According to the LEGO Principle. So don't hesitate to check it out. Also, the use cases shown in the tech tip can also be programmed with our IDS Peak API. There is a C++ code sample in the installation folder of IDS Peak that shows how to configure these use cases programmatically. It is located in the generic SDK section, and then you go to Samples, Source, CPP, and the sample is called LEGO Trigger. Now you might also wonder which features and modules your camera model supports and which use cases can be realized with your camera model. You can find an overview of which trigger use cases your camera supports or which camera family these use cases supports at the beginning of the tech tip. I won't go into detail concerning this in this video, but this is a good guideline when choosing a camera for triggering or considering a specific trigger use case. I hope the examples showing how to combine the different modules have made you curious to discover further possibilities for triggering and encourage you to let your imagination run free when it comes to your own application. Now all that remains for me to say is thanks for watching and happy triggering!